Welcome to Chemistry Solutions with Steve. This is a GCSE Combined Science Trilogy Chemistry paper, Higher Tier Paper 1. You can download all exam papers from the AQA website, and if you just look at the link below, you can follow that straight to that site. This can be used by teachers and students. For teachers, perhaps who are not specialists in science, or perhaps are science teachers but not specialists in chemistry. Students, you can use it in a variety of ways. You can print a paper copy and fill it in, stop the video at certain points, rewind, etc. You can sit the exam in one full sitting and then go back and replay, mark it yourself. The choice is yours. So we'll start with some general exam advice. You'll be given the exam and you'll be able to look at the front page and go through that front page before the examination continues. And what I suggest you do is go through each of the bullet points on the front page and you tick it when you've read it. You know, use a pencil and just tick each bit when you've read it. And that way you know that there's no information that's going to be any surprise. Another piece of equipment that you might find useful is a highlighter pen, and this will help you to highlight key words, command words, and number of marks available for each question. So I'll demonstrate this now. Question 1. This question is about electrolysis. A student investigated the mass of copper produced during electrolysis of copper chloride solution. Figure 1 shows the apparatus. There's figure 1, you've got an inert carbon electrode, a plus and a minus electrode, that's the anode and cathode, and a copper chloride solution. 1.1. Which gas is produced at the positive electrode, or the anode? And we've got 4 choices. Let's have a look at what we can see here. So we've got a positive electrode, that's the cathode, and anode, and we know that copper chloride contains copper 2 plus ions and Cl1 minus ions. So the negative chloride ions are going to be attracted to the positive anode. So as the chloride ions reach that anode, they will make chlorine. So, for 1 mark, you must tick the box chlorine. Question 1.2. Copper is produced at the negative electrode, the cathode. What does this tell you about the reactivity of copper? Tick 1 box for 1 mark. Copper is less reactive than hydrogen. Copper is less reactive than oxygen. Copper is more reactive than carbon. Copper is more reactive than chlorine. So what we must remember from our work on electrolysis, at the negative electrode, the less reactive element is discharged. And in aqueous solutions, the key to this is hydrogen gas. So if the element is below hydrogen, then the element itself is discharged. If the element is above hydrogen, then hydrogen is discharged. Therefore, copper is less reactive than hydrogen. Tick the first box. Next question. Table 1 shows the students' results. And here we have table 1 with 4 times, 1, 2, 4 and 5. Notice 3 is missing. And you've got 3 experiments for each of those times plus a mean. Determine the mean mass of copper produced after 3 minutes. If we go over here, 3 minutes is obviously between these two values here, and if we go from here to here, that increases by 0.6, and so one would assume that this one increases by 0.6. So if we add 1.2 to 0.6, we get 1.8 milligrams. Over the page, question 1.4. Calculate the mass X of copper produced in experiment 2 after 5 minutes. Use table 1 on page 3, and this is a 2-mark question. So what we need to do is look at table 2. Let's have a look at table 2. We've got to find this value X. So those 3 numbers there are divided by 3. That's experiment 1, 2 and 3. divided by 3 equals 3.06. The answers grid here. So we've got 3.02 plus 3.01 plus x equals 3.06. And we've got to find what x, or I've got to divide that by 3 and find out what x is. So we take the 3 up there and cross it over and multiply it with 3.06. That comes to 9.18. So if we look now, 3.02 plus 3.01 plus x equals 9.18. If we evaluate that, we get x is equal to 9.18 minus 3.02 minus 3.01, which gives us a final number of, for x as 3.15 milligrams for 2 marks. Question 1.5. The copper chloride solution used in the investigation contained 300 grams per decimeter cubed of solid copper chloride, dissolved in 1 decimeter cubed of water. The student used 50 cm cubed of copper chloride solution in each experiment. Calculate the mass of solid copper chloride used in each experiment. And this is a 3-mark question. Looking here, you can see that there's 300 grams per decimeter cubed. And we know a decimeter cubed is 1,000 centimeter cubes. So we need to find out the mass in 1 centimeter cubed and then multiply it by 50. So let's have a look at some numbers. So 300 divided by 1,000, 0.03 grams per cubic centimetre. Then we simply have to multiply that number by 50 and we will get our answer of 15 grams. So we get 1 mark for the first calculation, 0.03, 1 mark for multiplying it by 50 and 1 mark for the final answer of 15 grams. Right, question 2 then. This question is about sodium and chlorine. Figure 2 shows the positions of sodium and chlorine in the periodic table. And what you've got here is a little cut down version of the periodic table. So if we look at the periodic table, and underneath it is the first question. 2.1, state one difference and one similarity in the electronic structure of sodium and chlorine. So if we look across the top, we can label the groups 1, 2, 3, 4, 5, 6, 7 and 0. And we can label the periods down the side, 1, 2, 3, 4. And sodium is in group 1, and we know that's got 1 electron in its outer shell. And chlorine is in group 7, so we know it's got 7 electrons in its outer shell. A difference is different numbers of electrons in the outer shell, and we notice that the similarity is that they're both in the same energy level, or they've got the same number of energy level. So let's put that into an answer. So for a difference, sodium has 1 electron in its outer shell or energy level, whereas chlorine has 7 electrons. That's the first mark. And for a similarity, sodium and chlorine both have electrons in the 3rd energy level or shell. Question 2.2. Sodium atoms react with chlorine atoms to produce sodium chloride, NaCl. Describe what happens when a sodium atom reacts with a chlorine atom. Write about electron transfer in your answer, 4 marks. So we can look at a diagram here, and if we look at this little diagram, that the sodium atom has got this electron in its outer shell, which it transfers to the chlorine atom. So then we have a sodium 1 plus ion, which is 1 electron less, and a chloride 1 minus ion, which has got an extra electron. So to get our marks, we must write a sodium atom loses its outermost electron in the reaction. This electron is transferred to the outer shell of the chlorine, which now has gained an electron. So we get 1 mark for saying sodium loses and 1 mark for electron, 1 mark for saying the electron is transferred, and 1 mark for saying the chlorine has gained an electron. Question 2.3. The reaction between sodium and chlorine is an exothermic reaction. Complete the reaction profile for the reaction between sodium and chlorine for 2 marks. This is another bog standard reaction profile. The key is exothermic, so the products must be lower than the reactants and you must have this exact shape, a mark for the curve and a mark for the products lower than the reactants. Question 3. A student plans a method to prepare pure crystals of copper sulfate. Student's method is 1. Add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker. When the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. The method contains several errors and does not produce copper sulfate crystals. Explain the improvements the student should make to the method so that pure copper sulfate crystals are produced. And this is a 6-mark question. Now, this is an experiment you've done before, and really what this question is doing is just getting you. Can you remember the copper sulfate practical? Also, can you remember how to get maximum points? If you look at the bottom of the screen, here's the mark scheme from this question. Level 3, relevant points, identify, detail, logically linked. You know what to do, make a plan. So let's try and identify some of the errors here. Now the first one is that the student uses wants to make copper sulfate and the student is using calcium carbonate. Well, that's wrong for a start. That needs to be copper carbonate. Now, to make copper sulfate, you can't use hydrochloric acid, can you? Because that would make copper chloride. We need to use sulfuric acid. So let's write down this first improvement. The student should use copper carbonate instead of calcium. In order to make a sulfate, the student should use sulfuric acid, not hydrochloric. Okay, let's look at number 2. It says add a spatula and when the fizzing stops, heat it. This is wrong. What you should do is add a spatula of copper carbonate one at a time and keep adding until no more reacts. This is called adding to excess. When you do this, you will see some of the copper carbonate solid left in the bottom. So you've got a solid in that solution. So to get rid of that solid, you must filter it. So let's get that written down. The student must add the copper carbonate to excess, i.e. until no more will react and there is solid copper carbonate left in the mixture. Then you should set up a filtration apparatus with a funnel and a filter paper and filter the solution till it's nice and clear. In order to get crystals of copper sulfate, you must reduce the volume by about half by heating it and place it on a windowsill to cool. So to get the last section in, the student must then filter the mixture to remove the unreacted solid. The copper sulfate solution is gently heated to reduce its volume by about half and left on a windowsill to form crystals. Question 4. This question is about the halogens. 4.1. Write the state symbol for chlorine at room temperature for 1 mark. Well, we know the state symbols are S for solid, L for liquid, G for gas, AQ for aqueous. And you should remember from periodic table that chlorine is a gas at room temperature. So in the space provided, we put a lowercase g, and it must be lowercase, not a capital. 4.2. Figure 4 represents 1 molecule of fluorine. Complete the dot and cross diagram on figure 4, and here's figure 4. You've seen these before. You should only show the electrons in the outer shell for 2 marks. Now you must recall that fluorine is in group 7 of the periodic table, so it will have 7 electrons in its outermost shell. So each of those fluorines in figure 4 must have 7 dots and 7 circles. So let's put them in. You've probably been told that it's a good idea to put electrons in pairs as well. So if you go around the fluorine, you get 3 pairs of crosses, and then the 7th cross goes in the overlap area. Likewise for the second fluorine, the 6 electrons in 3 pairs and then the 1 in the overlap. Now those electrons in the middle, they can go anywhere on the line or inside the line for 2 marks. 4.3. A fluorine atom can be represented as, you can see it there, F with a 19 at the top and a 9 at the bottom. What is the total number of electrons in a fluorine molecule F2? And this is for 1 mark. And you must tick one box. Right, so let's look at this symbol here. This number here, the 9, this represents the number of protons and electrons. It's the same number. So fluorine has 9 electrons, right? So if you've got a F2 molecule, you must have 2 atoms of fluorine, so you must have 2 lots of 9, which is 18. So tick the box for 18 for 1 mark. Point 4. Aluminium reacts with bromine to produce aluminium bromide. Complete the balanced chemical equation for this reaction for 2 marks. Now what's missing is the formula for aluminium bromide. So how do we come up with that? Well, if you know it off by heart, brilliant. If you don't, aluminium is a 3+ ion, a positive ion. Bromine is a Br1-. So remember, in a compound like aluminium bromide, there can be no overall charges. So to cancel those aluminium 3+s, we must have 3- from the bromine. So this is going to give us the formula AlBr3. Now we can begin to balance. Now you notice in front of the AlBr3 there is a 2. That means there must be 2 of everything in front. So let's look at the aluminiums. If there's 2 aluminiums here, we must have 2 aluminiums on the left hand side. To the aluminium bromide, there are 2 lots of bromine, so there are 3 bromines, so 2 lots of 3 is 6. So if we go back to the bromine gas, there are already 2 atoms in a molecule, so to make that into 6, we multiply that by 3. So we would get 1 mark for the correct formula of aluminium bromide, and the second mark would be for the correct balancing. Over the page to question 4.5. When chlorine reacts with potassium bromide, chlorine displaces bromine. And there's an equation. Cl2 plus 2kBr goes to Br2 plus 2kCl. Explain why chlorine is more reactive than bromine. And this is a 3-mark question. So if we plan our answer out here, chlorine, we know from the periodic table, is higher up in group 7, so it has a smaller atomic radius. Therefore, chlorine's outer electrons are closer to the nucleus. If they're closer to the nucleus, they're more strongly attracted. And because of the number of energy levels, there's less shielding. So chlorine can gain an electron into its outermost shell more easily, therefore it's more reactive. So if we look at the final answer here, we get 1 mark for saying it's got a smaller atomic radius, 1 mark for saying the electrons are closer to the nucleus, 1 mark for less shielding. There's also a mark for saying that the chlorine can gain electrons more easily. And there are 4 points there. Any 3 of those would do for 3 marks. Question 5. This question is about structure and bonding. 5.1. Figure 5 shows part of the structure and bonding in diamond. Here's figure 5. You've seen this figure many times in your lessons and notes. Explain why diamond has a high melting point for 3 marks. So let's take a look at the diagram. You can see here that these black circles are in fact carbon atoms, and these lines are covalent bonds. So there are lots and lots of carbon atoms, lots and lots of covalent bonds, and these covalent bonds are very strong. So let's jot down some ideas. Diamond has lots of covalent bonds in a giant structure. These bonds are very strong, the covalent bonds. Therefore, we will need a lot of energy to break these very strong bonds. So let's look at our written answer. The carbon in diamond has many very strong covalent bonds between the atoms, 1 mark. These are arranged in a giant structure called a macromolecule, 2 marks. Therefore, and that's the key word, it requires a great deal of energy to overcome these bonds. 3rd and final mark, back of the net. The page 5.2. Figure 6 shows part of the structure and bonding in sodium chloride, NaCl. And here's a model. And we've got the chloride ion, which is the large circle, and a sodium ion. Explain the conditions needed for sodium chloride to conduct electricity for 3 marks. So, ionic compounds can only conduct electricity when they are in solution with water or when they are molten. Why is this? Because the ions have to be free in order to move and carry the charge. So let's look at our marks. For ionic compounds to conduct electricity, the compound must be dissolved in water, 1 mark, or molten, 1 mark. Only then will the ions be free to move and carry the charge, and the final 3rd mark. Question 5.3. Figure 7 shows the structure of sodium. Figure 7 here, you've got this picture, you can see it in front of you. Describe how sodium conducts thermal energy for 3 marks. Let's annotate this diagram. You can see I've drawn some little red circles in there. And what they represent are electrons. And in metals, these electrons are free to move. They're delocalized. And they can move, and therefore they can transfer the energy through the metal. So let's look at the marks available. Metals have delocalized electrons. That's underlined because you must have that written down. When thermal energy is applied to metals, these electrons are free to move and they transfer the energy through the metal. 6. Group 2 metal carbonates thermally decompose to produce a metal oxide and a gas. 6.1. Give the formula of each product when calcium carbonate, CaCO3, is heated. And this is a 2-mark question. This question is based on the topic about the conservation of mass and when products give off gases during a reaction. Carbonates, when heated, will always decompose to give a oxide and a carbon dioxide gas. So, the answer for this question is calcium oxide and carbon dioxide for 1 mark each. 6.2. The relative formula mass Mr of a group 2 metal carbonate is 197. The relative atomic masses of carbon are 12, oxygen 16. Calculate the relative atomic mass Ar of the group 2 metal in the metal carbonate and name the group 2 metal. And this is for 3 marks. Now group 2 metal carbonates all have the same formula, MCO3, where M is the unknown metal. Now we're given the Ir for carbon, which is 12, and oxygen, which is 30. So M plus 12 plus 3 times 16 equals 197. So we end up with M plus 60 equals 197. Then if we evaluate this, we end up then with M equals 197 minus 60 equals 137. So the relative atomic mass of the metal, the Ar, is 137. Now we'll need the copy of the periodic table that we've been given in the examination. And we'll look down the group 2 metals to find a metal that's got a relative atomic mass of 137. And here it is, look, barium. So, the answer for the metal is barium. 2 marks for working out the relative atomic mass and 1 mark for barium. So, over the page. Figure 8 shows the volume of gas produced when a different group 2 carbonate, W, is heated. And figure 8 is this graph. So we've got the volume of gas on the y-axis and the mass of the group 2 metal carbonate on the x-axis, the mass in grams, the volume in cubic centimetres. 6.3. Calculate the gradient of the line in figure 8 and give the unit. This is a 3-mark question. So we need a gradient with a y divided by x value. Now to do this, what we do is we try and make it easy for ourselves. So if we look along the x-axis, let's pick a number that's going to be easy to divide. It could be 1 or it could be 2. Let's choose 2. Now number 2, 2 grams goes up to this point here. So this is where we need our construction line. So we use a pencil and ruler, we draw a line across like so. And then we just use the scale to work out where that line intersects the y-axis. So 300, 10, 20, 30, it's about 334, 335, something like that. And that's the cubic centimetres. So if we go back to the x-axis, we've already decided we're going to drop our construction line down to 2. So here we are. So now we're going to do some maths in the answer space. So we've got a gradient equals the y over the x, which is 334 divided by 2. That comes out at 167. Now the units are simple. We just take the units on the y, which are centimetres cubed, the units on the x, which are grams, and we put the centimetres cubed divided by grams, or we could even do centimetres grams, centimetres cubed grams to the minus 1. So to get 2 marks, you must write where the gradient says 167 for the working out, and for the unit you get 1 mark, centimetres cubed per gram, or centimetres cubed grams to the minus 1. Right, over the page, 6.4. 24 decimeters cubed of a gas is produced when 1 mole of a group 2 carbonate is heated. Determine the relative formula mass of group 2 carbonate W. Use figure A, and this is for 4 marks. Now, this is an extremely challenging question because we have to try and work out how are we going to use the graph. So we've got to choose a volume on that graph. Now, if you look, 24 decimeters cubed is 24,000 centimeters cubed. So if we can think, well, if I can say take 240, that would be a fraction of 24,000, wouldn't it? So I'm going to draw a construction line across at 240 centimeters cubed and drop it down to the x-axis. Now that comes out at as we said earlier, 240 centimetres cubed is a fraction of a decimeter cubed. So if we do 240 divided by 24,000, that is equivalent to 1/100th of a mole. Okay, because 1 mole is 24 decimeters cubed. Back to the graph, if we look at the construction line, it comes down on the x at 1.45 grams. So if we multiply this back up, 1 mole will be 100 times 1.45 grams, which, when we crunch that on our calculators, comes out at 145. So the relative formula mass is the mass in grams of 1 mole. So that's how we know 145 is our relative formula mass. As I say, if you've got anywhere near 4 marks on this, you did very well. A scientist does 2 tests on 4 white solids labelled A, B, C and D. Test 1. Adds the sample of solid to distilled water and stirs. Test 2. Measures the pH of the solution after test 1. Table 2 shows the results, and you can see here a raft of results for each of these solids. And these results are really comparing 2 things. Solubility, which is indicated in the appearance after stirring, and the pH. Now the question is, identify the solids A, B, C and D. Explain your answers, and this is a 6-mark question. As with most of these 6-mark questions, we have the mark scheme here for question 7.1, and if we're looking to get the maximum marks, we should be aiming for level 3, so we need to give relevant points. That means getting the 4 answers correct and logically linking to form a clear account. So we'll come to that in a minute. So the appearance after stirring is giving us a clue as to the solubility of the oxide in water, and the pH column is telling us whether the solution formed is acid, alkali or neutral. Now you may well recall that metal oxides, when dissolved in water, form a pH greater than 7. Non-metal oxides, when dissolved in water, form a pH less than 7. Now, if a solution has a pH of exactly 7, it's neutral, but it probably tells you that the solid did not dissolve at all. In other words, it's totally insoluble. So, if we look at this one here, pH 14, that is strongly alkali. So that indicates that the substance has dissolved quite a lot. And pH 9 here, that is also alkali, but perhaps indicates that the substance hasn't dissolved as much. What's more important is that it tells us that A and C are both metal oxide. Now, if you look at B in red here, this pH of 3 tells us that this oxide is a non-metal. And because it's dissolved, there's no solid left behind, it is highly soluble. And finally, pH 7 here for D tells us that it is insoluble. So let's go down to table 3 and have a look at some more detailed information that we've got on solubility. The 4 solids are magnesium oxide, phosphorus oxide, silicon dioxide and sodium oxide. So if we look at these 4 solids, we know that magnesium oxide is a metal oxide, phosphorus oxide is a non-metal oxide, silicon dioxide non-metal oxide, and sodium oxide is a metal oxide. So this data tells us that magnesium oxide is just soluble, that sodium oxide is very soluble, phosphorus oxide soluble, and silicon dioxide insoluble. Now we can begin to start matching these up to the 4 compounds. So if we look at magnesium oxide and sodium oxide, they've both got a pH greater than 7. Magnesium comes out at 9 and sodium oxide at 14. So from our data so far, sodium oxide must be A and magnesium oxide must be C. Also from the table above, phosphorus oxide, which is quite soluble, comes out with a pH of 3. So this certainly must be a non-metal oxide, but it must be B because of its solubility. And finally, silicon dioxide has no solubility whatsoever, so this in turn must be the pH 7, so this must be solid D. So the first thing we do is write these down on our answer page here. The A sodium oxide, B phosphorus oxide, C magnesium oxide, D silicon dioxide. And finally here, what we've got is the written out answers in logical form. So A is sodium oxide because it's got the highest pH 14 and is very soluble in water. B is phosphorus oxide because the solution of B has the highest and only acidic pH of 3 and it's also quite soluble. C is magnesium oxide because it has a pH of 9 and it's hardly soluble at all. D, silicon dioxide because it's not soluble at all and therefore has a pH of 7. Question 7.2. 10 centimetres cubed of solution B is added to a beaker. Distilled water is added to the beaker until the final volume in the beaker is 1000 centimetres cubed. The pH of the solution is measured before and after distilled water is added. Table 4 shows the results, and here's table 4. The volume of the solution in the beaker on column 1, and in the second column, the pH of solution. So the pH of 10 centimetres cubed of the solution is 3, and the pH of 1000 is X, and we have to calculate the value of X, and this is a 2-mark question. The first thing we look at is this number here from 10 centimetres cubed to 1000. That works out at 100 times dilution. So the original 10 centimetres has been diluted 100 times. That when you dilute an acid by 10 times, the pH goes up by 1. So by very definition, if you dilute by 100 times, the pH number must go up by 2. This will mean that the pH will go from 3 up to 5. So to get 2 marks for this question, you must say that there's a dilution factor of 100, and for each factor of 10 the pH will increase by 1, therefore the pH will go from pH 3 to pH 5. Question 8. This question is about iron. Iron reacts with dilute hydrochloric acid to produce iron chloride solution and one other product. 8.1. Name the other product for 1 mark. Okay, we know a metal and acid produce a salt plus hydrogen when they... So to get 1 mark for this question, we must write hydrogen in the space provided. 8.2. Suggest how any unreacted iron can be separated from the mixture for 1 mark. Now, iron is a solid, so when you have iron or a solid in a solution, the best way to separate it is by filtration. So to get 1 mark for this question, you should write filtration or filter. Next question. Magnesium reacts with iron chloride solution, and here's a equation. 3Mg plus 2 FeCl3 goes to 2Fe plus 3 MgCl2. 8.3. 0.120 grams of magnesium reacts with excess iron chloride solution. Got some relative atomic masses, magnesium 24 and iron 56. Calculate the mass of iron produced in milligrams, and this is a 5-mark question. Now, this is a difficult question. There's a lot involved, but there is 5 marks. And if you set out your working out in a methodical way using my table method, you can pick up marks along the way, and hopefully you'll get all 5. Now, if we look at the question, the only 2 products or the only 2 chemicals that we really need to consider are magnesium and iron. So we lift those from the equation. We've got 3Mg gives 2Fe. And the table method is quite simple, really. You just put down the left-hand side mass Mr. mole ratio, and we're going to use that formula triangle, Mr. Moles with the mass on his head. You might have other acronyms to help you and little phrases to remember that, but that's mine and it works every time. So we fill in as much data on the first column. So we've put 0.120 grams, that's how much magnesium we've got. The MR is 24. So using the formula triangle, the number of moles is the mass divided by the Mr. And that's why we put them in that order. And if you follow that through, you get as your answer for the number of moles 0.005. Then we have to look at the ratio. From the equation, the ratio is a 3:2 ratio. So for every 3 moles of magnesium, there are 2 moles of iron being made. 3:2 ratio is a bit tricky because you can't just double it or half it if you like in a 2:1. But if we take the number of moles from the working out in the equation, 0.005, and we times that by 2/3, because the ratio goes from 3:2. And if you calculate that, you end up with 0.00333. We can then put in the MR for iron, the atomic mass of iron, 56, and back to the formula triangles, Mr. Moles with the mass on his head. And this time we're going to work out the mass of iron, which is the Mr, times the mole, which is 56, times 0.0033. So when you crunch that on your calculator, you get 0.1866. Now, if you're looking carefully, that's in grams, and the answer needs to be in milligrams. So to convert from grams to milligrams, we multiply by 1,000, and we need to round this up to 3 significant figures. So if we multiply 0.187 by 1,000, we get 187 milligrams. So for mark allocation, we're going to get a mark for the correct number of moles of magnesium, a mark for the correct number of moles of iron, a mark for the mass of iron produced in grams, rounded up to 3 sig figs, and the final 5th mark is to convert into milligrams. 5-mark question. Over the page, 8.4. Explain which species is reduced in the reaction between magnesium and iron chloride. It's the same equation, 3Mg plus 2FeCl3 gives 2Fe plus 3MgCl2. Your answer should include the half equation for the reaction. This is a 3-mark question. So whenever we get half equations and reductions, we think of that good old acronym OIL RIG. Oxidation is loss, reduction is gain, and of course we are referring to electrons. So let's look at the ions involved. So if we look at iron chloride is made up of an Fe3 plus ion and a Cl minus ion 3 times. Now those ions, those Fe3 plus ions, have been made into metallic iron atoms with no charge. So in order to do that, they must gain electrons. So the Fe3 plus gains electrons to make Fe ion. So if we refer to oil rig, those ions are gaining electrons, so reduction is gain, so the iron 3 plus ions have been reduced, and that's the species to which it's asking us to talk about in the question. Species is nothing to do with biology or anything like that. It's just to do with atoms, ions, molecules, chemicals. They're often referred to as species. So if we look at the answer, to get our 3 marks, iron chloride consists of Fe3 plus ions and Cl minus ions. In the reaction, the Fe3 plus ions gain electrons from the magnesium. The Fe3 plus is therefore reduced, and so the half equation is Fe3 plus 3 electrons goes to Fe. So there's a mark for saying that the Fe3 plus ions gain electrons, a mark for saying that the Fe3 plus is reduced, and then another mark for the half equation. 3 marks, back of the net.